Thank you, Dr. Braun, for the kind introduction. But as you said, morning y'all, my name is Cadet Charles McLaughlin, and my summer undergraduate research presentation is titled Microwave-Assisted Methylation of Lipids Extracted from Archaeological Pottery. So our overall project goals were to develop and refine a lipid residue methylation method for application in the analysis of archaeological pottery fragments, otherwise known as SURPs. So the hallmarks of a method should be reproducible and efficient, cost-effective in nature, and to accommodate a large dynamic range of lipid residue concentrations. However, my summer research overall goals were to gain facility with methodologies, the extraction of FAMEs, the synthesis and analysis of those FAMEs. To confirm prior group results, I am working from the data from former Cadet Halpern and former Cadet Emma Funkhauser, and from Faith McDonald, and to refine the method that we already have in order to increase effectivity. But essentially this means to reduce the number of steps, improve and confirm our extraction process of FAMEs from a reaction mixture, to explore alternative synthesis pathways. This includes microwave accelerated methylation, to remove sources of trace contamination that we encounter. So whenever we're dealing with irreplaceable artifacts and we're utilizing a destructive method like the one I'll show you, is that we need to make sure that we ensure the robustness, the reproducibility, as well as minimizing and removing sources of bias. So here's an example of some of our shards that we would crush, and once we crush it, we don't get them back. So we need to make sure that we can ensure our good, molecular target. So our target molecule is lipids, and lipids are a robust class of biomarkers. They're unmatched in resistance to degradation, such as oxidative. So triglycerides exist in nature as fats and oils. In each plant and animal species, they synthesize them using a unique combination of fatty acids. So for example, this table right here shows different food sources: maize, sunflowers, pumpkins, bisons, and then olive or olive oil, which is our main lipid we'll be using, and the different fatty acids up here and the percent composition of them in the different food sources. And so fatty acids are labeled according to the number of carbons in their chain with respect to their number of double bonds. And for example, an 18-1 fatty acid indicates that there's a chain of 18 carbons and 1 double bond. Our synthetic strategy: we need a simple volatile target that will provide key fatty acid ratios whenever we analyze it. So we must facilitate the derivatization of triglycerides, diglycerides, monoglycerides, and free fatty acids. So we chose an acid catalyzed methylation as our derivatization. And the pros is that both transesterification and esterification can occur. However, this includes a longer reaction time that requires higher temperatures. Base catalyzed methylation, however, requires lower temperatures and almost no heat to react. There's a pro is that acid catalyzed methylation does not react across double bonds. This means that we're not going to get any products that we don't want, whereas BF3, which is a common base catalyzed methylation process, can methylate across double bonds. And if you add too much of a base, we can cause saponification or the creation of soap, and that will not be good for what we're trying to do. But another pro is that we can convert free fatty acids as well as glycerides into FAMEs, whereas base catalyzed methylation only converts glycerides into FAMEs. And the problem with this is that with working with pottery shards, we can have glycerides as well as free fatty acids. It could be like 16-0 like stearic acid or what have you. And if we had a base catalyzed methylation, we'd only be working with glycerides, meaning that we would be ignoring and not being able to fully see the picture of our pottery shard. So therefore, acid catalyzed methylation is our go-to synthesis. And here's an example of the reaction. Methanol HCl is our catalyst and excess methanol, but the overall mechanism of the reaction is that we will protonate the esters on the triglycerides, which will then lead to a nucleophilic addition of the methanol onto our triglycerides, followed by 2 separate proton transfers, and then the elimination of an alcohol, which will happen over the course of 3 different times in order to produce our FAMEs, and glycerol will be a byproduct from the base molecule, the triglyceride. Our analysis, we use GC-FID and GC mass spec. Here are my conditions that we used whenever we were analyzing our samples. Method confirmation. So the first part of confirming our method is to demonstrate reproducibility. Affirm our own technique and the techniques of previous researchers. We have to develop confidence, or quote unquote gain lab hands. This is the biggest part of microscale synthesis. Experiments that we ran to confirm our method was to determine the limits of detection using a wide range of olive oil as our lipid, and to see quite unquote how low could you go. And we also have to confirm the optimal catalyst concentration of methanolic HCl, which was determined to be 7% around, and we did a range of 5 to 9%, and this is based on previous data and what we confirmed within our research. However, we have a general procedure. So step 1 is crushing the pottery. Step 2 is lipid extraction / desorption. This is an example of a triglyceride that we'd be extracting from the pottery. And it is worth noting that within my research, we only focus from step 3 and on. We are hoping to move into step 1 and step 2 as we pursue more methods. But methylation, acid catalyzed transesterification of our desorbed lipids. Step 4 is our 3-step hexane extraction of the FAMEs and our calcium chloride addition, which acts as a drying agent to remove any excess water before we extract it. So then we have our FAMEs, evaporate under nitrogen, reconstitute with hexane. We're ready to go to GC or GC mass spec for analysis. This table represents the experiment where we found our optimal MEOH HCl concentration. We found optimal conversion of lipids into FAMEs at around the 7% methanolic HCl. So ideal conversion of lipids into FAMEs occurred within this range. However, this is a much subtler trend than what we noticed in previous data. Previous data indicates a much sharper trend towards the 7%, so this will take some more time in which we have to fine tune, and we'll have to run a couple more experiments to get a more pronounced trend. This shows our limits of detection experiment, or as we call it, the limbo experiment. How low can you go? And so as we see a decrease in the volume of oil. As we see a decrease in the volume of oil, we see a decrease in peak area, which means we were converting less and less and redetecting less and less. However, with our data, instead we would expect to see a more linear trend to go straight through 0. This one we saw a more logarithmic approach, which also requires more testing. More previous data sets showed a more linear downward trend, so this is something that we had to this is a balance of time and also moving on to get to other parts of the experiment, but we did see a trend. However, this will take more time in order to do it. And we did it over a wide dynamic range, all the way down to 0.5 microliters to 25 microliters. So for example, we did it down to 0.02 grams and also down to 459 micrograms of olive oil. And we also gained proficiency with the techniques whenever it comes to methylating, extracting, and analyzing our product. Method optimization, this is the fun part. So we refine and optimize our synthetic strategy. This includes reducing steps and increasing efficiency, verifying our extraction steps of the FAMEs from the reaction mixture, and to explore microwave-assisted methylation technique. The experiments we ran were reaction extraction step analysis. It's pretty fun to say. 1-step extraction versus a 3-step extraction versus an overall 5-step extraction to see how much product we're extracting from a reaction mixture. Microwave-assisted methylation. We focused on time, temperature, and percent methanolic HCl concentration to find a rough idea of an optimal parameters in order to get optimal conversion of lipids into FAMEs. Controls, trace contamination analysis. We screened our solvents, our reactants, and our equipment for any possible contaminants. Product extraction verification. This table shows that after 1 extraction, we had 89 we had right around 90% product extraction from our reaction mixture, but after 3, we had close to 99.8% product extraction. Then after our 5th extraction, we were below detectable limits. And here is an example of our extraction peak. We see an exponential decrease in the amount of product in our sample after extraction. And so we verified our 3-step extraction of FAMEs after methylation, and we improved our FAME recovery by 9.8% from a previous 1-step extraction. We had first only used a 1-step extraction, move up to a 3-step extraction, and it gained 9.8% increase in extraction. Microwave-assisted methylation time. So what we did was, over a course of data, we found that between 15 and 25 minutes, optimal conversion occurs between that range of lipids into FAMEs. So this indicates our optimal microwave time is between 15 and 20 minutes. This was, however, a little bit rushed, so this is something we'll have to go back and explore further in order to find a more optimal time range and to fine-tune it. Microwave-assisted methylation versus our heating block. So our microwave is our new technique and versus our traditional heating block. What we see is an average of 63% increase in peak area between our microwave-assisted methylation and heating block. We also see around a 250 millivolt increase in peak height from our heating block to our microwave-assisted methylation. So pros, our microwave increases our peak area by 63% and reduces reaction time by 33%, going from an hour for our heating block down to around 20 minutes for our microwave. However, heating blocks allows for batch processing of samples. We're able to react multiple samples at once as compared to microwave one at a time. And so microwave samples must be done individually, whereas heating block samples require a longer reaction time and results in lower average peak area. So we're trying to figure out a trade-off that balances both cost, waste, and also effectiveness. For our controls, we noted contaminants. So this peak from our GC mass spec of some of our samples indicate that there's a 9-octadecyanonitrile, which is a plasticizing agent. And what we see is contaminants from micropipette tips, and our method for doing is that we would perfuse the tip with our solvents for 30 seconds, then we would add them to our reaction vessel, and then we would use the same tip and repeat the perfusing in addition. And what we see is a significant decrease from our first extraction down to our second and third extraction. So as the tip was washed over time, the contaminants were flushed out. However, we did notice that just using a pipette tip for the first time, you will have some contamination of your sample. And our reaction vessel caps. So we used to use rubber-lined reaction vessel caps whenever we were heating during methylation, and this area is from contaminants from the rubber. And so what we noticed that rubber-lined reaction vessel caps contain fatty acids regardless of if they are synthetic or natural rubber, and they would react and form FAMEs which appeared in our desired range, and it can bias our results. And PTFE caps or polytetrafluoroethylene caps are required for reaction vessels and storage containers because because solvents do not leach from them, meaning that we can have cleaner spectra. Conclusions of our controls is that plastics are a source of trace contaminations, plasticizers, free fatty acids, etc. And our current method removes all plastics from the procedure except for auto pipette tips. However, this is a balance of cost, efficiency, and reduction across contamination as opposed to using, say, micro glass syringes. Solvent storage. Volatile solvents can leach contaminants from non-PTFE storage container caps. So therefore, our solvent stocks are replenished daily and kept in glass inhalation vials, and we just use it as a use-by-use basis that we replace every single day. And when possible, PTFE caps are utilized. However, caps are expensive, and thus a cleaning procedure is being developed in order to reduce waste and cost. And so our overall conclusions for the project was that we developed a facility with method through the confirmation of previous research. As Happy Jones would say, we gained our lab hands. We further improved method through the addition and confirmation of a 3-step extraction. 3 extractions obtained 99.8% of the product from the reaction mixture as compared to around the 90% extraction from the single extraction step. We began exploration of microwave-assisted methylation. That we observed a 63% increase in peak area for identical 7% methanolic HCl concentration with a third of the reduction in reaction time. And we also identified possible contaminants. We noticed trace contamination, identified the contaminants, determined their source, and proposed new methods to remove sources of contamination within our techniques. FAME's fortune in the future. So going back to the future, if you will, microwave-assisted methylation. We want to confirm our reaction time range and narrow it down, and we want to explore different methanolic HCl concentrations and reaction temperatures in order to maximize our peak area conversion, or maximize our peak area. We need to develop a robust glassware and cap cleaning strategy, reduce waste and per sample cost, explore microwave assisted desorption. So this pottery is found from the Greenshield site, and this is an example of our first parts of our method, step 1 and step 2 of the pottery crushing and lipid extraction from the pottery. We would like to port our microwave assisted desorption over to lipid extraction in order to reduce extraction time for our pottery. And we also want to apply methods to the completion of the Greenshield site. So the Greenshield site is a historic Indian site that was occupied by the Arikara tribe during the late 18th and early 19th century. It was located on a high Pleistocene terrace above the Missouri River floodplain in North Dakota. And so, acknowledgements. I'd like to thank Lieutenant Colonel Braun for his tireless devotion and guidance along the way. And be here now, G. Thank you. Noah Halpern and Emma Funkhauser and Faith McDonald for working on their previous research. I'd also like to thank Colonel Harrison and Cadet Andres Hernandez for showing us how to effectively use the Discover microwave accelerated reaction system. Thank you for also letting us mooch off some of your supply of test tubes. Cadet Dean Warren for showing me how to use the mass spec from time to time, and Emma Cameron for for what you're about to see on the next slide. And I'd also like to do a big thank you to the chemistry department SURP program for making this possible. Any questions? And here are my sources real quick.